Start.
Hello everyone. So we are here today to explain our project in the subject of design and analysis of algorithms. And the topic we have chosen is Huffman coding, and the project title is chat compression using Huffman coding. So today we generate a huge amount of text data every second through chats, social media, emails, and applications. So more data means more memory consumption and higher bandwidth for transmitting that data. So can we go to the next slide? So there is a need of compression, right? Because data is so large, we need a way to reduce its size without losing its information. Compression helps us store and transfer data more efficiently by reducing the number of the bits required. So why Huffman coding and what is Huffman coding? We'll know. So in our project, we use Huffman coding, which is one of the most effective and most best, it's a more effective and efficient way for compression techniques. Like there are many other compression techniques, but they are not for text. There is only Huffman coding for text. So it assigns shorter codes to frequently repeated characters and longer codes for um, non-repeated characters. So that's how Huffman coding works. And now let's see step by step in the next slide. So now let us look into the workflow of Huffman coding. So firstly, to do Huffman coding, we require a frequency count. So if you have an example of any set of characters, the frequency of that is the number of times a character repeats. Like the repetition of the time is its frequency. And the second step is to build minimum heap. To build minimum heap, we just arrange those frequencies in order so that it will be easy for a next step, that is construction of a tree. So for the construction, we take the minimum number of frequency and then we sum them up together to create a parent node. And likewise, we create all the other nodes. So after creating our tree, we now generate binary codes. Generation of binary codes is really simple. The left side of the tree will be with 0. The right side of the tree will be 1. So the left ones will be counted as 0 and right side will be 1. So like that, we generate binary codes. And the last and final step is to encode and store. So encoding, as we generated the message, we write that as easily and then like that we encode it. So from here, my friend Karthik will continue.
I myself,
Hi,
Karthik.
myself Karthik.
Here I am
Here I
explaining
am
about
explaining
the
about the
Huffman
how
coding
Hoffman
works with a
coding works
simple
with a
chart
simple
message.
chart message.
The message
The
we
message
are
we are
using is
using is
hello here.
hello here.
First, we have to
First, we
count
have to
how
count
many
how
times
many
each
times
character
each
appears.
character appears.
H appears
H
once,
appears
E
once,
appears
E
once,
appears
I
once, I
appears
appears
twice,
twice,
and
and
O appears
O
once.
appears once.
Using these
Using these
frequencies,
frequencies,
Hoffman
Hoffman
coding
coding
generates
generates
shorter binary
shorter
codes for
binary
more
codes for
frequent
more frequent
characters and
characters and
longer codes
longer
for
codes for
less
less
frequent
frequent
characters.
characters.
So the
So the
Hoffman codes
Hoffman
for
codes
the
for the
this message
this
becomes
message becomes
I is equal
I
to
is equal
0,
to 0,
H is equal to
H
1
is equal to
0,
1
E
0,
is equal
E is
to
equal to
1 1
1
0,
1
O is
0,
equal
O
to
is
1
equal
1
to
1.
1 1 1.
Finally, we will
Finally, we will
encode this
encode
message
this
using these
message
codes.
using these
The
codes. The
compression
compression
output
output
becomes 1
becomes
0,
1 0
1 1
1
0
1 0
0
0
0
0
and triple
and
1.
triple
This
one.
shows
This
how
shows
text
how
can be
text can be
efficiently
efficiently
compressed using
compressed using
Hoffman coding.
Hoffman coding.
We will
Now
go to the
we will
next
go to the
slide.
next slide.
Here we can see
Here we
that
can see that
actually the
actually the
hello message
yellow message is
contains 40
contains
bits.
40 bits,
But after
but
using
after
the
using the
Hoffman coding,
Hoffman coding, it is
it is
converted
converted into
into
11 bits.
11 bits.
So we can
So we can
almost
almost
save
save
72%
72
of
percentage
data
of data
size
size
while
while
compressing this.
compressing this.
We will go to
We will
next.
go to next slide.
Compression becomes
Compression becomes
more
more
even
even
useful when
useful
applied
when
to
applied
real
to
chart
real
data.
chart data.
First,
First,
real world
real
charts
word charts
includes
includes
common words
common
like
words like
I,
I,
okay,
okay,
repeated characters
repeated
like
characters like
emojis,
emojis,
etc.
etc. These repetitions helps achieve better compression. Second, in large chart blocks, the amount of repetition increases, more repetitions means better compression ratios. Because frequent words or characters can be given very short codes. Finally, Hoffman coding can be applied either to each message individually or the entire chart sections, depending upon the application requirements. Now, coming to the advantages and limitations. Now, let us see advantages and the limitations of the Hoffman coding. First, we will go to the advantages. It produces an optimal prefix-free code, and meaning no code is a prefix of another. It provides lossless compression. Nothing will be lost while we will compressing this message. It works very well for text-based start where repetition is common. Encoding and decoding are also very fast while compressing this. Now going to the limitations. We need to store the code table along the compressed data. Otherwise, decode isn't possible. If all characters occur with the same frequency, then Hoffman coding is not efficient. It is not suitable for multimedia files or encrypted text because those unusually do not have predictable frequency patterns. Now, my friend Nani will take over.
Good morning, everyone. Myself, Nagmani Shankar. Today, I want to explain about the time and space complexity of this Hoffman coding. And I designed one prototype, and I will show this. This is my prototype. I will show how this will works. Now, if you want to enter some message, here you can check. Here we use 17 characters, and this contains 136 bits. And our message is and hello, how are you? And here zeros are used 3 times and spaces are used 3 times. And here H letters are these are the frequency of the table, and it will shows how many characters are repeated. Here it will show, and this is the Hoffman coding. After using the Hoffman coding, it will convert into a code. Here spaces value is code is 111, and it will repeated this length is 3, and here a character is 001, and this is 4, and like this we are after if letter is H, and here H, where is H? Here 001, here we need to take 001, and here next is E. Like that we are converting into the code. And after here we can check out original bit size is 136, and after compressed it will contains 55 bits, and now compressed size is 40, and total space saved means we saved 59.6. That like this prototype will works, and finally that user can receive that message. And next I want to explain about the time and space complexity of this. Here first of all we need to follow 4 steps to find out the time and the space complexity. And here first need to build a frequency table, and next need to build a minimum heaping tree and build the Hoffman coding, and finally generate the Hoffman coding tree. And here we are taking from users n number of characters. We don't know how much characters we are taking, and here A, B, B, C, C, D, D. And here A repeated 3 times, and B repeated 2 times, and C repeated 2 times, D repeated 2 times. Here we are taking n number of characters after we are converting into frequency. And here that frequency is unequal numbers, and distinct characters or unequal characters. That's why we are here we are storing order of D. And here we are storing order of n because we are taking n number of characters. Here we are taking order of D. This is distinct characters, that's why. And here we are taking here this we want to apply the heap sorting. We need to convert our array into already sorted array. That's why we are taking order of n log n. Here we are taking n equal characters. That's why we are taking order of D log D. Next one is our 2 steps are completed and 3 steps are completed. And here we need to find out the final time and space complexities. And here first we are taking order of D. We are taking n number of characters after we are converting into a frequency table, that is order of D unequal characters. And here after sorting our array, we are converting n log n to D log D. And last we are storing this into order of D and distinct character messages. And here final output is here order of O of n is taken, and here order of cancel, and here d log d is the final time complexity, and next one is the space complexity. Here frequency table is order of d. We are taking unequal characters, that is the frequency table, and we are taking order of d. And the heaping is heaping also we are taking order of d. And Hoffman coding tree contains a order of d only. That's why we are taking totally space complexity order of d only. And here last in this Hoffman coding benefit is always it is best case, average case, and worst case. It will only order of d log d, and this is the final time completion. And our friend is will give conclusion.
Now
Now going to the
That's
conclusion.
project.
Hoffman coding is highly effective for compressing short messages. It helps us to save storage and reduces the transmission costs, especially in the applications like messaging apps like using WhatsApp, but it is not work because it is encrypted. It is simple to implement in most programming languages. And finally, Hoffman code forms in the basis of many modern compression standards used today. Thank you.